Hello everyone, welcome. In this video, we are going to talk about the model of the universe, and we're going to explore the evolution of our view of the universe. Model of the universe have two kinds. We have the geocentric model and heliocentric model. In heliocentric means having the sun at the center of the universe, with the earth and other planets revolving around it. The term comes from the Greek word helios, which means sun. Many astronomers believe in heliocentric model, such as Aristarchus, Nicolaus Copernicus, Galileo Galilei, and Johannes Kepler. In the geocentric model is a supersede astronomical model of the universe that places the Earth at the center, with the Sun, Moon, stars, and planets orbiting around it. The term comes from the Greek word geo, which means Earth. And also, there are four astronomers who believe in geocentric model, such as Eudoxus, Aristotle, Claudius Ptolemy, and Tycho Brahe.
Eudoxus geocentric model. Eudoxus of Cnidos was an ancient Greek astronomer and mathematician who proposed an influential geocentric model of the universe around 400 BCE. Eudoxus of Cnidos proposed a model to explain the motions of the five known planets of his time: Mercury, Venus, Mars, Jupiter, and Saturn. These planets, along with the Sun and the Moon, were central to his geocentric model of the universe. He believed that the planets move in circles around Earth, each on a separate concentric sphere. Eudoxus' model explained retrograde motion by suggesting that the planets' spheres were not all moving at the same speed. The apparent backward motion could be explained by the relative motion between different spheres. Retrograde motion occurs when a planet, as observed from Earth, seems to move backward in its orbit for a period of time before resuming its normal forward motion.
Aristotle model of the universe just like Exodus. Aristotle's universe is geocentric, which places the sun and other planetary objects around Earth. He added the universe is finite in terms of space and eternal in time. Aristotle believed that the Earth was round, and he also believed that objects in space move in perfect circles, which he considered the perfect shape. He thought that comets must exist inside of the Earth's spheres because they didn't move in perfect circle.
Claudius Ptolemy's geocentric model of the universe. Ptolemy adopted Aristotle's geocentric theory of the universe. Ptolemy's model was most highly developed geocentric model of the time that widely accepted for over 1,400 years. However, it was eventually superseded by heliocentric model such as those of Nicolaus Copernicus, which placed the sun at the center of the universe. Ptolemy's model was able to accurately and predict planetary position and eclipses. He accounted for the apparent motion of the planets around the Earth by assuming that the planets moves around the spheres called the epicycle. The center of epicycles move on a large spheres called different.
Tycho Brahe geoheliocentric model. Tycho Brahe's geoheliocentric model, also known as the Tycho Neck system, was a model of the universe where the Earth was at the center, with the Sun and Moon revolving around it and the other planets revolving around the Sun. Brahe's model was popular at first but was eventually replaced by the more accurate Copernican model within about 100 years. However, Brahe's model was appealing to those who wanted to move away from the older view of the universe, but weren't ready to accept the idea of the sun at the center. Brahe's model was accurate enough to predict the position of the planets.
Aristarchus' heliocentric model. Aristarchus, of Samos Greek, astronomer who first attempted to create a heliocentric model of the universe. He was the first person to attempt to calculate the distance of the Earth to the Sun. He conducted this by measuring the angle between the Moon and the Sun and applied the principles of trigonometry. The ratio between the distances is equivalent to the cosine of the angle. Aristarchus calculated that the Sun was 19 times further away from Earth than the Moon. Aristarchus described Earth as a body that rotated daily around an axis and revolved annually around the Sun. The stars were fixed in a large sphere with the Sun at the center. According to him, the Sun and fixed stars were at rest while the Earth and other planets revolved around the Sun in a circular path. Aristarchus' model was rejected because it went against the prevailing belief that the Earth was the center of the universe. His calculations were also wrong due to a lack of precise instruments.
Nicolaus Copernicus' heliocentric model. Nicolaus Copernicus' heliocentric model is the first widely accepted idea that the Sun is at the center of the solar system. Copernicus made observations without a telescope, using only a naked eye and simple instrument, taking the apparent movement of the stars in the sky into account. He explained that the Earth spins around its axis. His model able to successfully explain the observed changes in the phases of Venus. Copernicus' model was based on the work of earlier astronomers, including Indian astronomers and cosmologists. He was disturbed by the failure of Ptolemy's geocentric model to follow Aristotle's requirement for uniform circular motion of all celestial bodies.
Galileo Galilei was an Italian astronomer, mathematician, and inventor who supported the heliocentric model, which places the Sun at the center of the solar system with the Earth and other planets revolving around it. He invented the telescope and proved the Copernican hypothesis. Earth rotates on its axis and revolves around the Sun. And here are Galileo's astronomical observations: the moons of Jupiter, the phases of Venus, the surface of the Moon, the Milky Way, sunspots, the rings of Saturn, and planet are disk. The moons of Jupiter. Galileo discovered 4 moons orbiting Jupiter, now known as the Galilean moons: Io, Europa, Ganymede, and Callisto. This was revolutionary because it showed that not everything in the sky revolves around Earth, challenging the geocentric model of the universe, which held that all celestial bodies orbit Earth. The phases of Venus. Through his observations of Venus, Galileo showed that the planet goes through a series of phases similar to the moons. This was strong evidence for the heliocentric model of the solar system proposed by Copernicus, which argued that Earth and other planets orbit the Sun, not the Earth being the center of the universe. The surface of the Moon. Using his telescope, Galileo observed the Moon's surface in great detail, revealing mountains, valleys, and craters, which contradict the Aristotelian view that the Moon was a smooth, perfect sphere. This reinforced the idea that celestial bodies were not perfect and unchanging as previously believed. The Milky Way. Galileo also observed the Milky Way, and with his telescope he discovered that it was made up of countless stars rather than a single cloud of light. As had been previously thought, this provided further evidence of the vastness of the universe. Sunspots. Galileo observed spots on the sun, which he reported in his work Sidereus Nuncius, or Starry Messenger. These sunspots showed that the sun was not perfect, as earlier traditions held. They also demonstrated the sun's rotation, as the spots appeared to move across its surface over time. The rings of Saturn. Galileo first observed Saturn with his telescope but misinterpreted the rings as ears or handles on the planet. It wasn't until later astronomers like Christian Huygens used more advanced telescopes that the rings were properly understood. Planet or disk. One of the Galileo Galilei's key astronomical observations was that the planet appeared as disks rather than pinpoints of light, which was the case for stars. This observation provided important evidence that planets were distinct from stars in the sky, and was one of the pieces of evidence Galileo used to support the heliocentric model of the solar system. Johannes Kepler heliocentric model. Johannes Kepler was a German astronomer who supported the heliocentric model of the solar system, which places the Sun at the center of the universe and the planets orbiting it. Kepler's work improved on the model developed by Nicolaus Copernicus and led to the heliocentric system being more widely accepted. He showed mathematically that Copernicus' idea of a sun-centered system worked well if a uniform circular motion was replaced with an even but predictable motion along off-center ellipses. The law of ellipses. The orbit of every planet is an ellipse with the Sun at one of the two foci. Prior to Kepler, it was believed that planets move in perfect circles in accordance with Aristotle's and Ptolemy's geocentric model. However, Kepler discovered that planetary orbits are not circular but elliptical, or oval-shaped, with the Sun positioned at one focus of the ellipse, not at the center. This was a radical shift in our understanding of the solar system. The law of equal areas. A line drawn from a planet to the Sun sweeps out equal areas during equal intervals of time. This law explains that planets do not move at constant speed in their orbits. Instead, a planet moves faster when it is closer to the Sun and slower when it is farther from the Sun. This law reflects the conservation of angular momentum. When a planet is closer to the Sun, the gravitational pull is stronger and the planet accelerates. When it's farther from the Sun, the gravitational pull weakens and the planet decelerates, thus balancing the area swept out over time. The law of harmonies. This law establishes a relationship between the distance of a planet from the Sun and the time it takes to orbit the Sun. Specifically, the farther a planet is from the Sun, the larger the semi-major axis, the longer its orbital period. This means that outer planets like Jupiter or Saturn take much longer to orbit the Sun than the inner planet like Mercury or Venus. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. The mathematical formula t is proportional to the cube of a times the square root of t, where TTT is the orbital period, the time it takes for a planet to complete one orbit around the Sun, and AAA is the semi-major axis of the planet. The third law allowed Kepler to demonstrate that the orbits of planets are not only elliptical, but that the motion of each planet is also governed by a universal relationship, which holds true for all planets in the solar system. Thank you for listening.